Okay, cool. So today we'll talk about active learning. But before doing active learning, I want to mention, first of all, so just a reminder that homework number 6 is due on Friday. And also your project review is due on Monday. And it's a reminder that you guys should definitely talk to your TAs. Yeah? Which of you has a mentor TA? Definitely talk to them and get them to help you. Okay? Cool. And actually one comment that I want to make, so some of you asked me, so when I did SVM, I didn't go for the derivation of the dual. But I did post lecture notes by Andrewing. I mean, you are welcome to read the derivation of the dual, but you are not required to know it. Okay, it's just because I think it's beyond the scope of the course. If you are curious, you can definitely read it and talk to us about it. Okay, cool. So today we'll talk about active learning, but I want to take a minute before doing so to talk about, to come up with more general remarks about semi-supervised learning, which is what we talked about last time. Okay, so I mean, both active learning and semi-supervised learning, we discussed, are motivated by the fact that for most modern machine learning applications, we have such massive amounts of data that basically it's impossible to have humans or experts to annotate or label all the data for our learning task at hand. Yeah? And so this is the motivation. I mean, that's why a lot of the research, a lot of the exciting research in modern machine learning has been on designing learning techniques that somehow most effectively utilize all the available data, but somehow, in the same time, minimize the need of expert or human intervention. Okay, and semi-supervised learning and active learning are two topics that have been well studied, and there has been significant progress. And they're exactly trying to achieve is to somehow best utilize the available data, but minimize the need for expert intervention. Okay, and I just want to spend a couple of slides summarizing semi-supervised learning. Just a quick reminder of semi-supervised learning is, so in this case, as typical, we have some source of data. We have a distribution over the underlying data. And we assume that in the training phase, in addition to a small set of labeled examples, which are drawn IID from the same, from this underlying source, and labeled according to a fixed but unknown target function. So in addition to this small set of IID labeled examples, we also assume that the algorithm gets to see large amount of unlabeled examples coming from the same source. Okay, and the goal is, as typical, is to try to find a classifier that has a small error rate with respect to points that come from our underlying source. Okay, so that's a typical, typical goal when we do machine learning and we assume that there is a distributional learning scenario. Okay. And last time we discussed that what unlabeled can do for us, right, in this setting, right, when unlabeled can help us in drastic ways is in the case where somehow our inductive bias or belief about the world involves not only beliefs about how the target function looks like, for instance, is a linear separator, but when our inductive bias also involves beliefs about how the target function relates to the underlying data distribution. Okay, that's the moment when unlabeled can become helpful in very substantial ways. Okay, and we discussed three very different types of technique, very different types of semi-supervised learning techniques that people have looked at that are based on very, very different assumptions about how the target function would relate to the underlying data distribution. Okay, and it'll take me 2 minutes to go through all of them. It's interesting to see all of them on one slide. Okay, so the first one is the semi-supervised SVM algorithm, which is due to Thorsten Joachim's. And here the underlying belief is that not only the target function separates, say, positive examples from negative examples, but it does so by a large margin. Okay? And then the corresponding optimization problem, we talked about it, is what we do if we see we have as input a small set of labeled examples, also lots of unlabeled data. And what we do, we just find a classifier that gets the labeled data right, or almost right, and is trying to maximize the margin over both labeled and unlabeled points. Okay, that's transductive SVM, or semi-supervised SVM, and it's based on the belief or the assumption that the target function does not cut through high-density regions of the space. In other words, has a large margin. Okay, with one belief, that makes unlabeled data informative. Now, a different, very, very different type of belief that makes unlabeled data informative, I'm going to skip to the third one here, is the belief that underlies the co-training learning algorithm. Okay, and we've been through this in detail last time. So here we think about problems where we have two natural set of features, right, for our problems. Like for web page classification, we might use the words inside the web page for classification, or we might use the words from the hyperlinks pointing to the web page from other web pages. right? So here, right, we're thinking about, so in this co-training world or multi-view learning world, we are thinking about problems where we have two very natural types of features that are somehow sufficient for correct classification principle and consistent, agree with each other, okay? And we've seen that if this is underlying belief about the target function, how the target function relates to the underlying data distribution, then conceptually speaking, in the iterative co-training view, unlabeled data can then help us to propagate learned information from one view to another, right? Or we can also think about, so this is iterative co-training view, but we can also think about just doing direct optimization. This is like just one-shot optimization, where what we can do, we just try to find a pair of functions, h1 and h2, that would get the labeled data right, and would agree as much as possible on unlabeled data, or get almost all the labeled data right and agree as much as possible on unlabeled data. Okay, and I just want to make a comment. Last time when I talked about theoretical guarantees for this work, I said that, well, the initial guarantees are above the case when the underlying distribution satisfies the independence given the label assumption or the expansion assumption, but actually this is not needed for co-training to be useful. So actually, when you have independence given the label or expansion, when co-training provides drastic benefits, we need only constant number of labeled examples to learn well. But actually, co-training is also useful if the distribution is less nice. Maybe it's a cluster of distributions that each individual satisfy independence given the label, then it's still helpful. We need more label samples, but the co-training idea is still helpful. I just want to make this comment. Last time I only talked about independence given the label. Okay, cool. So a different belief, right? So this in the co-training world, here the belief is that we have these two views that each agree with each other, and they are in principle sufficient for correct classification. And then unlabeled data becomes helpful. And as you can see, this is very, very different from the margin-based type of assumption, right? So the large margin assumption that underlies the transductive SVM. Okay. Now, we also spent a little bit of time last time talking about the very different type of assumption. And actually, Travis will go through that in recitation in more detail. A very different and very interesting, actually, widely used class of semi-supervised learning algorithms are those based on similarity-based semi-supervised learning algorithms. So here, somehow you assume that we have as input a similarity function, and let's assume that our similarity function is so good that we believe that similar points must have similar labels. Okay? Now, this makes unlabeled data informative, because what we can do, we can create a graph where all the points in the graph, all the nodes in the graph are my data points. Most of them will be unlabeled, like the green ones over here are unlabeled, but I'm also going to have some labeled ones. Okay, and then algorithmically what I do, I will try to partition the graph in a way where all the points of the same label, like these two blue points, go into the same part, and moreover, the weight across the part is minimized, right? Because like the underlying belief is that two similar points must have similar label, so if I have an edge between two points, that means that they are similar, so when I partition the graph, I want to make sure that I have very low weight across the cut, right? In order to satisfy the underlying belief that similar points must have similar labels. Okay, so this, as you can see, and there are very interesting ways, very interesting types of partitioning algorithms for doing so. Yes?
I have one doubt. In the self-consistent rules case, if the rule is like only 90% correct and 10% wrong,
yeah.
when you use it to propagate it to the next H2,
yeah.
the error would multiply.
Yeah, so that's actually right. So I mentioned this comment that I made last time, right? You weren't here, but I made this comment. Yeah, I know him so well. He always asks the smartest questions, so it's easy to notice when he's not in the room. But yeah, in any case. So right, so I did say that last time, right? So that's actually one of the problems with iterative co-training, right? So, so when you do iterative co-training, you can propagate kind of, once you start propagating wrong information, you might basically, you might not be doing so well. And actually, when I was a student, I did some experiments with this, and you can show that, for a while, like if you do iterative co-training for a while, the error of the combined classifiers goes down, but at some point starts going up, because of this reason, for iterative co-training, right? But I mentioned there are some guarantees you can give nonetheless. Like there are some concept classes that you can learn, like intervals on the real line, or rectangles in high dimensions. So those are concept classes that you can learn. They are called from positive examples only. And they are the property that whenever you predict, you say positive, you are confident about the label. Okay, and so if you have such learning algorithms, they may not predict always. They might predict only like a small fraction of the times. But if when they predict they are confident, then co-training would be safe. right? So, and actually we did have a paper, I had a paper in IPS of 10 years ago, or 11 years ago, where actually I was analyzing exactly this type of algorithms that are, so either, right, when they predict positive, they are confident about their label, they might not predict often, but when they predict, they are confident about the label, then this problem that you are mentioning, noise propagation, doesn't happen. There are also a different class of algorithms called reliable, useful algorithms, where just have the property when they predict, they are correct always. So if you have such algorithms, then code training is safe, and you don't propagate noise. But if these algorithms only exist for very simple classes, so in general it's true, yeah, noise propagation is a problem with iterative code training. Okay, but that's why actually, so when I discussed code training last time, I also discussed this multi-view view of code training, so one-shot optimization, where I'm trying to just find two classifiers that get the labeled examples as well as possible, and plus agree on the unlabeled data, that is less prone to noise somehow, I think. Yeah, but you're totally right. Iterative code training can suffer from noise propagation if we are not careful. Okay, cool. So as you can see, but so right, my point here is that basically in the semi-supervised learning world, unlabeled data is helpful if we have beliefs not only about the form of the target function, so our inductive bias doesn't involve only the form of the target function, but how the target function relates to the underlying data distribution. Okay, and we've seen very different ways in which we can express this by maybe the target function is a large margin, or maybe the target function has a property of self-consistency or agreement, or maybe the target function corresponds to a small cut that, right, in the similarity-based semi-supervised learning. Okay, now you might ask, can we extract a more general principle that can then help us write down generalization guarantees about when unlabeled data is helping me and by how much? And the answer is yes. And the key point here is if you think about it in all these methods, if you truly believe that the word is right, if you truly believe, say, for example, the large margin assumption or the self-consistency assumption, then what unlabeled data can do for us can help reduce the search space from the whole set of classifiers down to only those classifiers that will satisfy our belief once we see unlabeled data. Right? So maybe it can help us reduce our search space from the whole set of classifiers down to only those classifiers that have a large margin, and it's something that I can verify once I see unlabeled data. So it's kind of an abstract prior or abstract belief or inductive bias that becomes concrete once I see unlabeled data. Okay, so this is what happens when the belief is truly satisfied, right? When I truly believe that maybe I have a large margin or maybe I have this self-agreement. Now, if this is not quite right, because obviously we have an inductive bias, but it's not always quite right, so maybe almost right, right? The right way to think about what unlabeled data can do for us is, conceptually speaking, it will help us to reorder the functions in the search, to reorder the search space somehow. And so the functions that satisfy our belief heavily will be higher in the ordering, right? So basically, once I see unlabeled data, I can, this classifier, blue classifier over here will be higher in my ordering if my belief is about large margin. Okay, and so then implicitly what we are doing, kind of, if we reorder the functions, then we are kind of biasing the search towards these functions that satisfy our belief, that are more compatible with our belief. Okay, and if our belief happens to be right and the ordering happens to be nice, then we can get drastic benefits from unlabeled data. Okay, so this is what unlabeled data can help us do in semi-supervised learning. Okay, and then there's the key insight, and then we can then use this insight to then extend the classic PAC model or the classic statistical learning theory framework for supervised learning to then talk about, to basically provide a general model in which you can talk about how much data, unlabeled data do I need for learning, how much labeled data do I need for learning, when is labeled data helping me reduce dependence, when is unlabeled data helping me reduce dependence on the number of labeled examples, and by how much, and so on. Okay, and this has been done. Okay, and then this framework can then help you think about designing new semi-supervised learning algorithms and also just analyzing the existing algorithms. Okay, cool. And actually the survey I posted online for the semi-supervised learning, I posted online a survey by Jerry Zhu, and actually he does describe all the existing semi-supervised learning techniques by using this viewpoint. Which I think is a nice way to think about what happens when you have unlabeled data. Okay, and actually I'm just not going to go through these details today in the class, but I want to make a point that actually Tom spent a lecture talking about semi-supervised naive Bayes, kind of, right? And it turns out that actually we can also fit the semi-supervised naive Bayes within this viewpoint. Okay, and actually in the survey, Jerry Zhu does so. So if you can think about it, there is actually, you can also think about just doing reordering the functions so that the functions that you are more compatible, the functions you really care about are higher in the ordering, and then you need much fewer labeled examples to learn well. Okay, so you can read about this in the survey. Definitely think about it, how it connects to the viewpoint we've been talking about. So, I mean, the point is that this viewpoint is super general, kind of encapsulates everything you could hope for unlabeled data. Okay, so but that's semi-supervised learning. Today, my lecture today was, I wanted to focus it on a different, very exciting topic, namely active learning. So actually, any questions before I go on? Because I'm going to go to active learning next. Okay, cool. So then I'll just go to active learning. Right, and this is one of the topics that many people think it's the future of machine learning, active and interactive learning. So, and I agree with that. Good. So here, so in every field we've been talking about so far, when you use human supervision, right, like passive supervised learning or semi-supervised learning, we somehow were in a world where the algorithm was a little bit passive. So we didn't have any choice about which examples to be labeled, right? So we assume that when I actually went at the beginning of the lecture pictorially through what semi-supervised learning is, and then if you remember there, I assume that the labeled examples that I get are drawn IID, are random examples drawn from the underlying distribution, and they're just labeled by the expert. So I'm assuming that the labeled examples that I get are just random examples drawn from the underlying distribution. They are labeled. Okay? Now, what active learning does, so in active learning, and more generally interactive learning, so what we want to do is to have the algorithm be more active and take a more active role on deciding which examples to be labeled. Okay? Why? Because hopefully, if we do so, then we can learn with much fewer labeled examples. We can do even better and achieve higher accuracy by using even fewer labeled examples. That's basically the hope of active learning. Okay, and you see it's a really interesting topic that has been well researched in both applications and foundations. And you'll see there are many interesting aspects to think about. It's a bit non-trivial. Okay, cool. So, and actually, so right, I actually also in terms of reading, so in addition to my slides and my presentation, I also posted online, I'll post online a survey by Sanjay Dasgupta. It's a bit of a more technical survey on active learning. It's called Two Phases of Active Learning. So actually Sanjay has been one of the people that helped kind of inspired people to try to think about putting active learning on solid foundations. So it's actually one of my favorite researchers. So this is a very nice survey, a technical survey on active learning. I also I'll put a link to some more practical survey by Burr Settles discussing what heuristics people use in practice for active learning. And also I will include also a small note that I wrote for the Encyclopedia of Algorithms, more algorithmic on active learning. Okay, so this is a topic, it's a very modern topic, so the books, the classic books like Tom's book or Bishop's book and so on, they don't even include this topic. But it's a very important topic and it's good to cover it. Okay, so let's go through the model slowly. So, oops, oh, what am I doing? Good. Have too many things around. Good. So let's go through the model slowly. Okay, so what is active learning, right? So there are two models to think about when we do active learning, and I'm going to go through both of them because they are helpful to describe various points, and they are very commonly used. Okay, so the first one is the so-called batch active learning, where as typical, we assume that we have some source of data, we have some underlying source of data. And here, what we assume is that first, the algorithm gets to see a large amount of unlabeled examples. So the same as we've done, had in semi-supervised learning, right? But as opposed to semi-supervised learning, now the algorithm has the ability to choose specific examples to be labeled, right? So it can go look at unlabeled data and then decide, oh, I want to request the label of this example. And then the expert to label that example. Okay? And then again, goes back, you get that information back, and then the algorithm thinks a bit more and says, well, I want the label of this example. And then the expert labels that example, right? So here the algorithm has the ability to use large amounts of unlabeled examples, but then it also has the ability to choose specific examples to be labeled. Okay? And at the end of the day, the goal is still to output a classifier of small error rate. Just as typical. right? So here the algorithm has the ability to use large amounts of unlabeled data, can pick specific examples to be labeled, and somehow the goal of the algorithm is to be smart, to be adaptive, to learn with much fewer label requests than if we didn't have the ability to be active. Okay? And right, so in order to achieve this, obviously the algorithm has to somehow pick, to ask for the labels of somehow very, very informative examples. Okay, so this is a batch active learning scenario where the algorithm has the unlabeled data given up front. Okay, as I mentioned, there is also another active learning scenario called the selective sampling active learning, or online active learning. Right, so we discussed online at some point in time, and somebody asked me how is online learning different from active learning. Okay, and let me describe kind of the combination of the two models. So now, as typical in distributional learning, we still assume, it's not an adversarial world, we still assume that there is some source of data, we still have a distribution where the examples come from. Okay, so if still have some underlying source of data, but then we are kind of in we get to, instead of seeing the unlabeled points at once, as we did in the batch active learning, we see a stream of unlabeled examples, and then when each unlabeled example arrives, we have to make right away a decision whether to ask for the label or not. Okay, and if we ask for the label, we get more information, we can update our state, otherwise that opportunity is gone. I cannot query the label of that example in the future. Okay, that's stream-based, that's selective sampling active learning or online active learning. Okay, and pictorially, here is a picture. So the first unlabeled example, x1 comes in, and the algorithm has to make a decision. Should I ask for the label or not? And let's say it asks for the labels, then the question goes to the expert. The expert gives a label, right, the label y1 for this unlabeled example x1. Then the algorithm uses that label to somehow does some computations, updates in his internal state, right? Does some learning. And then another unlabeled example x2 comes in. The algorithm has to decide, should I ask for the label of that example or not? Okay, and maybe say that for this example, we don't ask for the label, right? And again, the next day, or the next time step, another unlabeled example comes in. The algorithm has again to decide, should I ask for the label or not? Let's say in this case, we do ask for the label. The expert gives us the label y3 for the example x3, and everything repeats. Yeah? But then after not too many steps, the goal is still to output a classifier that has small error rate with respect to points that come from the same underlying source. And we also wanted to ask for as few label requests, as few label queries as possible. Okay? Yes?
So when you have let go of one example to be labeled, can you go back and ask for that?
No.
No.
That's, you have the opportunity just in that moment. Yeah, I mean, this is motivated by maybe if you have memory constraints, like sensors, that have very limited memory capabilities, you cannot store the example. Yeah?
Would you still have an idea in online active learning? Would you still know the distribution of the data?
You get it through this process. You can still keep some summaries, right? And actually, most of the algorithms for which you can prove guarantees about active learning actually can be implemented in this online scenario. Because somehow as the unlabeled points come in, you still get an idea about the distribution. You don't necessarily keep the unlabeled points, but you maybe keep some summaries. Or maybe you can even, let's say one case where you only keep summaries, another case you are allowed to keep unlabeled points, but you're not allowed to go back and ask the expert on those points. Yeah, more questions?
So if you have enough memory, would you prefer the first one versus this online active learning?
Yeah, potentially, yes. Yes, this one can also, if you design an algorithm in this scenario, maybe it also leads to computational benefits, right? I mean, yeah. So, right, if you have enough memory, you might want to use the batch active learning scenario, but if you think about it this way, and if you kind of only use the last examples to update your hypothesis space, this also leads to computational benefits, both in terms of memory and running time. Yeah, so it could be, yeah, more questions?
In terms of relevancy of the data, I would imagine that an algorithm like this would make new data coming in more relevant in terms of the fact that if, for example, past data, if for example, you're doing a search, right?
Yeah.
Past data seems to be less relevant than, let's say, current data.
Sure.
This would be more representative in that case, or more appropriate than the batch data.
Yes, I should just mention, absolutely, yes, that could be right. Actually, I should mention the way, for my presentation today, I want to think about distributional setting where I have a source of data and I want to achieve low error respect to a distribution. Actually, this online selective sampling has also been analyzed in kind of adversarial scenario where you try to minimize regret but ask for as few examples as possible. And so if those applications of the type you mentioned would fit perfectly that type of model, like search engine and so on. Actually, there's a nice line of work by Niccolo Cesabianchi. He's an expert in online learning, and he has exactly analyzed this type of online active learning under worst case instances, and I think also not quite distributional instances, and that would be a perfect model for the problem you mentioned. But for today, I want to think about, just to simplify, because I want to discuss what are the interesting aspects when you think about it more formally. I'm going to think about the case when where you have an underlying distribution and the points come from that source. Yeah, more questions?
Building on that question, if we are thinking about recency and non-recency, then the
if you're thinking about
recency of the like relevance, recent examples are more relevant, past are not.
Yeah.
Then we are defying our like assumption that they are drawn IIT.
But you put a different weight on them. Sure, you can do that. Yeah, you can weight them according to.
But if they are IIT, it doesn't matter whether they are relevant. Like the relevancy is same for all the examples, right?
If IID, that's exactly what I'm saying. If IID, you implicitly assume that the relevance is the same. That's why to model his question, I was saying you might want to use results from like selective sampling active learning that works under adversarial instances. That's exactly what I was saying. But maybe an intermediate thing would be to actually still assume a distribution, but somehow maybe when you compute the error rate, yeah. Now, actually, let me take it back. I think that for that problem, if you want to kind of, the model by Niccolo Cesabianchi, or like online active learning, where you assume adversarial instances, that's a better one. Cool, one more question, yeah? Yeah, well, we are going to still assume an inductive bias, right? In order to hope to do any learning, we're still going to assume that the target function comes from some class of functions, it's close to some class of functions. Not really, okay? But I'll go for some more for some more concrete examples, okay? But definitely we need to assume some inductive bias, we need to assume something about the target function. The target functions are arbitrary, can fit random noise, we're not gonna do any learning, right? We need to still put some inductive bias, and we're also gonna be in the distributional learning scenario. Okay, and then these are all perfect questions. What would we do in this scenario, right? Okay, cool. So these are the models, batch active learning, right, so batch active learning where we get unlabeled samples at once. This is what I had in the earlier slide, yeah? And also online selective sampling, where I still, for today, I just want to think I want to think about the case when there is still an underlying data source, and I care about doing well with respect to points that come from the data source. Cool, so. Okay, now you guys already probably asked those questions. Okay, so given this definition of active learning, okay, so what is a good active learning algorithm is one that is guaranteed to output a classifier of small error by asking very few label requests for most problems, hopefully. And ideally, we want to learn with much fewer label requests than needed in passive learning or even needed in semi-supervised learning, right? So we want to use a querying capability to learn well with very, very few, very little human or expert supervision. Okay, and so obviously to do so, we need to somehow choose to ask for labels of super informative examples, right? Okay, cool. So then the next question would be, which is a very natural question. Okay, so that's the hope, right? But it's actually maybe adaptive querying doesn't help at all. Does it help us or not? We first have to even understand, is adaptive querying helping us at all, right? If the answer is no, then maybe we shouldn't work very hard to design an algorithm, right? But it turns out that actually adaptive querying, so having the capability to ask for labels of examples of your own choice, actually does help. Okay, and this has been observed in practice, and also about 10 years ago, it has also been observed more formally for simple cases. Okay, so you can show simple cases where adaptive querying does help. In both practice, not simple, in practice has been shown in many applications that it does help, and also you can also show simple examples. Okay, and let's go for some of those. Okay, I'm going to start with the formal one because it's very simple and it will be a concrete example of what active learning can do for us. And yes, this example has been known for a long time. Sanjay Dasgupta wrote it nicely in a paper in 2004. Okay, so let's assume it's a toy example, but it makes a point that active learning can sometimes provide drastic benefits. Okay, so let's assume that we are trying to, our assumption about the world, as you're asking, is that, the instance space is a real line here. I have just one feature. Right? And let's assume that I believe the target function is a threshold function. Okay? Good. Then I claim that here active learning can help us substantially. Okay, so here I claim that actually if we are active, we can get an exponential improvement in label complexity over passive learning. So you can learn with exponentially fewer samples than required for passive learning. Just kind of interesting. You could hope for some benefits, but exponential benefits is like amazing, right? So it's nice to know that such examples exist. Okay, so do you guys see? Okay, let me walk you through the algorithm actually. So I'll just give you a hint and then you can help me recover the algorithm. Okay, so here's the algorithm. So I claim that what we can first do, get a number of unlabeled samples. So because let's think about the batch active learning because it's simpler to think about in this example. So I first draw a number of unlabeled samples. These should have been, by the way, the same color. In any case, these are all unlabeled. Okay? And now here's the question that I have for you guys. I have n unlabeled samples, and if I was picked n large enough so that if I have the true labels of these examples, I could achieve learning by just using finding an arbitrary separator that is consistent with those samples. Yeah, then this is one way to try to achieve learning, right? So I'm going to draw n unlabeled samples. Now, of course, in passive learning, I would ask for the labels of all those examples. If n is 1 over epsilon, then I know from things that we've been talking about, we are guaranteed to output a classifier over almost epsilon. Okay, but now I don't want to do that because I want to be active. I want to somehow ask for fewer labels, requests. Okay, and so what I'm going to do, I want to exploit the structure of my hypothesis space. Okay, and I want to be able to recover the labels of all these n unlabeled samples by asking much fewer queries. And I claim that here it's possible. So if I've drawn n unlabeled samples, I claim that we can, with only log n queries, recover a correct labeling of all these unlabeled samples. And how do I do that? Well, I'm going to exploit the structure of my hypothesis space. Okay, this has a very specific structure. So I know that, for example, if I query for the label of this example and I find out that it's minus, because my hypotheses are thresholds on the real line, then I'm guaranteed that if this example is minus, then so these two examples are minus 2. Okay, so this gives you a hint about how do you recover the labels of all these examples by only using log n queries. Okay, so somebody wants to volunteer to, yeah? Okay, cool. Now there is competition on answering. Great. Good.
So I have one question.
Yeah.
So we assume that the data is separable by...
Right now, let's assume, just to make the argument simple, we're going to assume it's separable. Turns out, yeah. Exactly. Perfect, right? So binary search. With binary search, I'm going to do binary search. And with log n queries, I'm going to recover the labels of this example. So what do? I pick the example in the middle and ask for the label. If it's minus, I'm guaranteed that all the examples to the left are minus. So I throw out half of my points, right? And then I'm going to pick I only have to focus to the right. Then I, again, pick the example in the middle, what's left. I ask for the label. I discover it's plus. It means I can discard everything. I know that everything to the right is plus, so I don't have to focus my search there. I only have to think about what happens in here. Just ask for the label there, and I'm done. Right? So each time I halve the number of points under consideration. Right? So that's why it's log n queries. Cool? Right? And this is, I'm assuming that they are separable. The target function is truly a threshold function. But there are ways to make it robust to noise. Okay, and actually, I mentioned this as I go later in the lecture. Actually, there are ways to get robust noise active learning algorithms for very, very general scenarios, which is nice. These are things that were not known 10 years ago, by the way. Cool. But anyway, so this is an example where if I draw n unlabeled samples, with only log n queries, I can recover the true labeling of these n unlabeled samples. And then what I can do, I can just output a classifier that is now consistent with the inferred labels. Okay, so then that way I got the labels of n IID samples drawn from underlying distribution by only asking log n queries. And now if I make n to be 1 over epsilon, then I'm guaranteed to output a classifier over almost epsilon. Why? Because this is a very simple class of functions, right? So the VC dimension here is 1, if you guys remember. It was one of my toy examples. The VC dimension is 1, and because the VC dimension is 1, I know that I only need d over epsilon samples. So then if I then output a classifier consistent with d over epsilon samples, I'm guaranteed to have almost epsilon. Remember, VC dimension was a measure of complexity. In any case, this is such a simple class of functions. If you have 1 over epsilon, the labels of 1 over epsilon IID samples from the underlying distribution, you are done. Just output a classifier that is consistent with them. Okay, cool. So here we can actively learn a classifier. Yeah, do you have a question?
These levels is 2, right?
Oh, it's 1 because I'm assuming that just everything to the left is negative, everything to the right is positive. It would be 2 if I allowed also, if I, there are 2 related classes. Here I'm assuming that everything to the left, yeah, if I allowed classifiers that also allow plus here and minus there, then it would be 2. But I'm making things simple. Okay, cool. So here this dimension is 1 because of this reason. Okay, cool. So this is an example where basically active learning only requires log 1 over epsilon label requests to output an epsilon accurate classifier. However, if you think about it, passive learning probably requires omega of 1 over epsilon requests to output a classifier over almost epsilon. Intuitively speaking, because somehow if this was my target function, if I didn't see label examples in these regions that are epsilon close, then I'm not going to be able to output a classifier over almost epsilon and to see the examples that I need roughly 1 over epsilon samples. So you can make an argument that passive learning probably requires omega of 1 over epsilon label requests. So this is a great example where active learning does amazingly well. It's an exponential improvement in sample complexity over passive learning. Okay? And this is for the noise-free scenario. I just want to also mention that you can also do the same when you have noise. What is your name? Vikesh. Okay, good. Cool, so that's nice. So there are some formal examples where active learning helps. Now how about practice? Okay, so like this is formal example, toy example maybe. How about what do people do in practice? Okay, and I want to start by mentioning some heuristics that people do in practice and problems with those heuristics. Because now in active learning we can suffer from the so-called sampling bias. So you have to really be careful. Okay? Cool. So let me tell you a heuristic that is very commonly used in practice. It's also nicely related to things that we've been talking about in the past couple of lectures. So that's something called uncertainty sampling. I'm just going to describe this heuristic by using a very concrete algorithm, namely the active SVM algorithm. Right? So we've seen the 2 lectures ago SVM, and we've seen semi-supervised SVM, today we're seeing active SVM. Okay? Cool. So, right, what is the active SVM algorithm? It's very, very natural. I mean, so what you do, you proceed in rounds. In each round, I'm actually going to describe it. Let me think. It might be easier. It's actually the same description would work both in selective sampling and batch. Okay, just doesn't really matter. The same algorithm would apply. Yeah, good. So, I mean, I'm somewhere in the algorithm, and I have a current guess of the target function, would just be in this specific active SVM algorithm will be the maximum margin separators on all the labeled examples I've seen so far. Yeah, that's what SVM does. And then when I'm trying to decide which example should I query for the label next, very natural is to try to query the example that is closest to the current separator. Yeah, why? Because maybe you're most uncertain about, right? If it falls close to the current decision boundary, maybe you're more uncertain about its label. Yeah, so that's why it's an uncertainty sampling based method. This is called uncertainty sampling method. Okay, let me be more concrete, just because it's good to think about it for a second. Right, so here, actually I have the batch version written here, and I have an example here too. So here, basically, you have as input first a set of unlabeled samples, right? In the batch version, a large set of unlabeled samples drawn from the underlying distribution. Okay, then, right, we go in round. What's going on here? Okay, good, right. So these are my unlabeled samples first, right? And then first what we do, we just start querying for the labels of a few random samples. So maybe I get these 2 negative examples and this positive example. I just pick a few random examples and ask for their labels. Okay, this is what I get here. Okay, and then I go in rounds. Okay, and say at the beginning of each round, first I'm just going to do what active SVM does. I'm going to find the classifier that maximizes the margin over the current set of labeled examples, over the labeled examples I've seen so far. Okay. So in this case, I'm going to get this separator over here, and this will be the normal vector to the separator. Okay, cool. Then I'm going to ask for the label of the example that falls closest to the current decision boundary, because somehow maybe I'm most uncertain about it. Okay, that's the intuition. Okay, good. So I'm going to ask for the label of this example, and then I'm going to have the highest uncertainty, and then I'm going to retrain. I'm going to, then once I get that example, I'm going to again find the maximum margin separator over all the labeled examples I've seen so far. Right? And then in this case, will be this separator over here. This is a normal vector. Okay, and then everything repeats. Then maybe I'll pick another point. I'm going to think another point that is closest to the current decision boundary that is unlabeled, like maybe this example, red example over here. I'm going to ask for the label and just everything repeats. Okay, so it's very, very natural if you think about it. Widely used. It has been proposed in, I see, so it has been proposed by Daphne Collin and Simon Tong in 2000, and has been widely used since then. I mean, it's very, when people try to use active learning for their problems, when they really don't have much choice, you know, it's a very natural heuristic to try to use it. You have to do something, so it's very natural to do this one. Okay, and so actually I did pick some examples. So for example, there is this nice work by Kristen Grauman. She's a computer vision professor at UT Austin, and she had an IPS paper, 2010 paper, so very recent paper, where she showed that on some both newsgroup data sets, so these are text classification data sets, and also vision data sets, this algorithm does great compared to random sampling. Okay, so for example, for newsgroups data set, which is a classic data set, she showed that, for example, this is the curve for random sampling. So he shows a measure of accuracy of where the higher the better it is. Right? And she looked, okay, so she considered she was trying to speed up the heuristic, right? Because in order to compute the most uncertain example, you have to scan for all unlabeled points, and she wanted to speed it up somehow. And she has some tricks to make it sublinear time. Okay, that's why she has 3 versions over here. But in any case, the active SVM will be one of these curves, and then this will be the passive SVM. And you can see that at the same label budget, active SVM somehow does better than passive SVM on newsgroup data set. Okay, so that's nice, encouraging. And also does better, but not as the gap is a bit smaller, does better, but not as great for a different image data set, something called CFAR data set, which is a data set that is very commonly used in computer vision. Yeah?
If the data is clearly separable by 2 clusters into 2 clusters, it would be, we don't need the random sampling as well. We can straight away start with the points which are closest.
If you have unlabeled data, if you have it truly clearly linearly separable by 2 clusters, you can just do semi-supervised SVM, and you need very few label samples. If in the case where it's truly separable by 2 linear separator of a large margin by 2 clusters, I think you could just do semi-supervised SVM.
Like the case you showed right now in the graph.
Yeah.
You can straight away start with the 2 points which are closest to each other in the different clusters, and then identify the classifier between them. So
yeah, but you don't know, right? Yeah, that's a true statement, right? But okay, so there could be a heuristic that you can try to apply if the data in that case, right? But you'd have to do some pre-processing first, right? So, yeah, you're right. In that specific case, you could do a different algorithm, like this one that you just mentioned, right? But on this CFAR data set, I'm sure the structure is much more interesting, and it's not like that. And so you want general-purpose active learning algorithms that you could apply in general cases, right? Yeah, and all I was trying to do here is to explain that this very natural heuristic, uncertainty sampling-based heuristic, active SVM heuristic, just does well on some data sets, okay? If the data is super nice, then you can do something even simpler. I agree with you. Good. But I want to make a very important point, actually. So it does work sometimes. So these heuristics do work sometimes. But we have to be incredibly careful, okay? Why? Because these myopic, greedy techniques can suffer from sampling bias. Okay, and a bias basically because at any moment in time we have some sort of set of labeled examples. Those labeled examples are not IID samples from the underlying source, right? We have a biased kind of, we are greedy, myopic, and this label sample that we get is a very biased label sample, right? And so basically a bias is created by the querying strategy, and as the time goes on in this, because you only query points that fall close to the current decision boundary, the sample is less and less representative of the true underlying distribution. Okay, so you might be doing actually in the selective sampling scenario, you might even be inconsistent, let alone achieve good label complexity. You might be achieving some classifier whose error rate is very different from the error rate of the base optimal classifier. Okay, and here is a cool example that comes from the survey by Sanjay Das Gupta that I linked on the website. Okay, just to be a bit concrete, just let's assume again, for simplicity, examples on the real line. Right, so here we have says that we have most of the distribution is in these 2 extreme points. So 45% of the negatives are here, 45% of the positives are here. Then let's assume that 5% of the positives are here, and then I have 2 little blobs here. One of them is negative over here, and one of them is positive over here. Now, if you only see a few random samples, then I claim that most of the points are going to be here. If you see like a couple or 3-4 labeled examples, most of them will be here and here. And when I do the maximum margin separator, then what I'm going to find is this classifier over here. And then as the time goes on and on, I'm going to keep querying in this region only. And basically, I'm going to somehow never going to query these points. I'm going to be confident that I'm right on them because I have no uncertainty on them. But I'm going to be wrong because I'm going to label them as negative when they should be positive. And in the selective sampling version, even if I get an infinite number of label requests, if I let the number of label requests go into infinity, then I'm going to output a classifier whose error rate is actually 5%, which is worse than the error rate of the best classifier, which is 2.5%. Okay, so basically this shows that active SVM, it can be inconsistent, which is truly bad. It's not, I mean, even if I see not many label requests, I might output a classifier whose error rate is truly bad compared to the error rate of the best classifier. So that says we have to be truly careful, and we have to go beyond the heuristics. Okay, yeah?
If each time you query for a label, you flip a coin, and when it's heads, you take a point at random, and the rest of the time you take the low.
Yeah, in this case, you'll be probably fine, but you can come up with some high dimensions, or you'll still be wrong. You'll be doing something wrong. You have to do something smarter. Yeah? How do you improve? That's my next point. Okay, perfect. Okay, and I have an animation. I'm going to skip it so you can guys go through it offline, showing what the behavior of this example on both batch and selective sampling mode. Okay, you can convince yourself that what I said is right. Okay, you can go through the animation offline. Okay, but as Kelly was saying, how can we do better? Right? Can we do something? Right, so okay, so basically the point of this example is that, sure, selective sampling, active SVM, uncertainty sampling, all these heuristics, and by the way, there is a family of heuristics. I just picked one of them to illustrate, but they all have the same problem, the sampling bias. Okay, so there is this family of heuristics that sometimes does work well, however, they don't, I'll show simple examples so they don't really fail, and the main problem is that this is the main problem in active learning. They suffer from the so-called selective sampling bias. And actually, I want to mention that this has been observed in practice too. So, I mean, this is a toy example, but people have written papers showing that this actually happens in practice too. So, for instance, here this was a case where we have this cluster, right? So, we have this is kind of keeps being our current guess, and we have this cluster of data points where our current guess has no idea that is wrong about the label. Somehow, our current guess is confident but totally wrong, right? So, that's the main problem that's been observed in practice. Okay, now what can we do? Can we improve the situation and can we come up with algorithms that are safe, right? I mean, even for algorithms that we didn't talk about in class, so actually I think most of the algorithms we talked about in class for supervised learning are safe algorithms. People can prove guarantees that they do well, consistency guarantees, so it's good to always think, I think it's good to use algorithms that are safe, okay. But active learning is one case where natural heuristics might not be safe. Okay, cool. And I just want to mention, just before going on, the main intention seems to be that somehow we want to choose informative examples, to ask for labels of informative examples. But in the same time, we also want to guarantee that the classifier that we output does well on random samples that come from the true underlying data source. Okay, cool. And the question is it possible? And it turns out that the answer is yes. And there has been a lot of research in the past 10 years on the topic, on the so-called disagreement-based active learning or safe active learning schemes. And now we have super general results telling us very general active learning strategies that would work in the presence of noise and for very general scenario, for arbitrary concept spaces. Okay, and I want to spend some time, like 10 minutes, 20 minutes talking about this. And also, explain the state of the art there and where we are right now. Okay, and I'm going to start for simplicity with the case when we have no noise, because it's simpler conceptually to think about. And I'm going to describe some of the algorithms that we can use. Right, so the way to think about these algorithms is where we somehow do a search for the hypothesis space. Right, so but there is also a very different family of algorithms we could imagine doing, like what you were mentioning, maybe cluster the data and so on. These are a bit different. These are more of the type, I have a hypothesis space, a class of function, maybe linear separators, or maybe the kernelized linear separators and so on, and I'm trying to find the best classifier from that class in an active learning way by minimizing the number of label requests. Okay, there's also a family of algorithms where you can first do somehow unsupervised learning and then decide what to do, and if I have time, I'm going to go through those too. For those who know a little less formally, so the work where we know safe algorithms is this one, where we do kind of a hypothesis space search. But those are important too, the other ones. It's an important research direction there. Okay, so I'm going to think about the case where, so I'm going to think about this hypothesis space search type of paradigm. So I fix a class of functions. If you want to think about it, it can be the class of linear separators. Okay, and I'm assuming it's typical that I'm in a distribution learning scenario, right? So I'm assuming that the data comes from underlying source, data distribution. Okay, and I assume that I have a target function. Okay, and for the next couple of slides, let me assume that the target function, for simplicity, comes from this hypothesis space H, truly. Okay, because it's easier to describe the algorithm in that case. Okay, now given this, here is a notion. I don't think we cover this in class. Tom typically covers this in his previous courses, but so far we didn't cover it, but turns out to be a very useful notion in this context. Okay, so once we have, so let me define something called the version space, which is crucial for this type of algorithms. And what's really a version space is we have some learning problem. We have seen some labeled examples, ID or not. And we can think about the version space of the hypothesis space H with respect to the labeled examples we've seen as just being the set of classifiers in my hypothesis space that are agreeing with the labeled examples we've seen so far. Yeah, in the case when the target function belongs to the class, obviously that version space will be non-empty, right? Because the target function itself, we're going to agree with all the labeled examples I've seen so far. And I'm assuming that these labeled examples will be labeled according to the target function. Okay, so basically, let me say it slower. So this is actually a definition due to Tom. Here, right, so we assume that we have a hypothesis space H, like linear separators. I'm going to give an example in a second, okay? But let me first describe the definition. So we have a hypothesis space H, like linear separators. Let's assume that the target function belongs to that hypothesis space. Now, given a set of labeled examples, which might not be ID, yeah, because in active learning, the sample that we get is not really ID. That's the main problem. So given a set of labeled examples labeled according to the target function, then the version space of H, given the set of labeled examples, is just the set of hypotheses that are consistent with all these examples. So just a set of classifiers H, a classifier H belongs to the version space if and only if agrees with all the labels I've seen so far. Okay, so here's a simple example to think about. So let's assume that the data, just for simplicity, we're thinking about linear separators in R2. Okay. And let's assume that the data, just for simplicity, because it makes my picture easier, let's assume that all the data points are just lying on the circle. Yeah? And the classifiers that I'm thinking about are homogeneous linear separators in R2. So this will be an example. Like this is a normal vector, and this is a classifier itself. Okay, now let's think about what's the version space. So let's assume that we get two labeled points. Maybe I know that these are positive. What is the version space here? Well, it would be the set of classifiers here that label these examples as positive. And I claim that in this picture will be like, how do I find those classifiers? Well, I'm thinking about this example, so this is a positive example, and I'm going to think about which classifiers are going to label this example as positive. And I claim that it will be the classifiers whose normal vector lie in this region. Okay, so if you think a little bit geometrically, right, so what are the set of classifiers, right? So this is a first positive example, and what are the set of classifiers that label this example as positive will be classifiers whose normal vectors will lie in this region. So for example, this classifier, like if I think about this as an example of classifier, right? This is a classifier, this is its normal vector, and this classifier labels this example as positive, so it will be in the versions, it will be a correct classifier for this example. Okay, and so now I can also think similarly about the other example. What is a set of classifiers that label this example, this other example, as positive? I claim will be classifiers whose normal vectors lie in this region over here. Right? And so now if I want to find classifiers that label both as positive, so then this will be classifiers whose normal vectors lie in this region. Okay, so that will be my current version space, given these two labeled examples. Okay, now given a version space, I can also think about what is a part of the instance space where they agree. Because when we're going to do active learning, if I have a set of surviving classifiers and the target function belongs there, and if I agree on the labels of certain examples, obviously I shouldn't query there. I shouldn't waste my queries there. Right? So that's why it's natural to think about what is the region of disagreement of the current set of surviving classifiers. Okay, and so the version space. Right? So if it's my version space, these are classifiers whose normal vectors are here, are the classifiers in my version space, you can pictorially draw what is the region where these classifiers disagree. And what's basically that would be a point is in the region of disagreement if there exists a classifier in my current version space that disagree about the label. If there exist two classifiers in my current version space that disagree about the label. Right? And if you think about it, basically, in this example, it will be just this region over here. Right? Because if I, for example, if I have a point in this region, right, if I have a point in this region all the surviving classifiers, like this one here will be a surviving one, it's an example of a surviving one. And if I have a point in this region, we're all going to say positive on that example, right? Maybe I can just use, for a second, my marker. Right, so the point is that, for example, this is my current version space, right? And I claim that, for example, if I think about an example that comes here, basically you can verify that all these classifiers are going to label it as positive, so they don't disagree, right? Similarly, actually, if I think about an example that lies here, all of them are going to label it as negative, right? If I think about a point that lies here, all of them are going to label it as positive, right? So you can just think what is the region where they disagree, where it is the region of the version space where there exists two classifiers in the version space where they disagree, and this will be exactly this region over here, these two parts. Okay, so then I can just define exactly this quantity. So given a set of classifiers, H, so I have, given a set of classifier H, I should have been the region of disagreement of the version space. We should just be in the version space. I should just write it in the disagreement of the version space. In any case, I can just define the notion of disagreement. Whoops. Right, so if I have a set of surviving classifiers like this guy over here, I can define the region of disagreement, which is just the part of the instance space where there exist two classifiers that disagree on that point. So a point is in the region of disagreement of a set of classifiers, like a point this point here is in the region of disagreement of a set of surviving classifiers, of a set of classifiers if there exist two classifiers in the set that disagree about the label. That's the definition of the region of disagreement. Okay, now this definition here is a very natural active learning scheme, but actually turns out to do surprisingly well in certain cases. It's a very non-aggressive, it's a very mallow-active learning scheme, but does well sometimes, and it's safe. Okay, so what we can do, we can keep basically, we can just have we first can pick a few points at random, and we just pick the classifiers that agree with those points as the current version space. And then we can go in rounds. In each round, we can think about what is the region of disagreement of the set of surviving classifiers. And then what we're going to do, we're only going to ask for labels of examples. So we're going to pick a few random samples at random, subject to being in the region of disagreement of the current set of surviving classifiers. We can ask for their labels, and then we can update our current set of surviving classifiers. Okay, and this is clearly better than random sampling, is better than passive learning because we are active, right? We discard as the learning goes on and on. We're not going to query from certain regions of the space. Okay, so here is more concrete the algorithm. So initially we're going to query a few random points. We're going to query the label of a few random points. We let H1 to be the current version space, a set of classifiers consistent with all these random points. And then we go in rounds. In round T, we're going to think about what is the region of disagreement of the set of surviving classifiers. Okay, and we're going to pick a few points at random subject to being in that region of disagreement. So we're going to pick from the conditional given the region of disagreement of a set of surviving classifiers. We're going to query for the label of those points. Okay, and then we're going to use those points, the labels that we get, to then update our version space. And then everything repeats. Right, so that's natural. It's an active learning algorithm. In the case where the target function truly belongs to my concept space, is actually a safe active learning algorithm. Right, and actually you can show that sometimes it does well. Actually, you can get exponential improvement in sample complexity. Okay, and I'm going to come back to this. Okay, let me just walk this through an example. Okay, let me just one more time show a quick example followed on the previous one. I was showing this. Right, so as I said, so let's assume that this was our current version space, right? We first got some label points, right? And this was our current version space. And this is, like if you guys remember, this is our regional disagreement. Like this blue part was the regional disagreement given the current version space, right? And now you can think about it. Then I pick 2 points at random subject to being in the regional disagreement, and I pick these 2 points at random. And they happen to be in the regional disagreement, right? So I pick them at random subject to be in the regional disagreement. I query their label, I get their plus, right? And then I can update my current version space, right? So for example, I can shrink, right? Because if I think about it, so this is the current version space, it's a normal, corresponds to the normal vectors of the current surviving classifiers. And if you think about it, for example, these classifiers over here, in particular the one that has normal vector, this is a normal vector, we're going to incorrectly label this example. We're going to label it as negative when the example is positive. Right? So then I can use this example to then shrink, and this example over here as well, to shrink the set of surviving classifiers. So the set of surviving classifiers becomes smaller, and so does the region of the disagreement. Right? Now this is my new set of surviving classifiers, the blue guys over here, and the region of disagreement becomes smaller. Right? And if you think about it, if the region of disagreement collapses quickly as you get closer and closer to the target, then this algorithm is going to do great. And it's an active learning algorithm. Cool. But this is the way it's described right now. So this is a very natural algorithm that actually is due to Cohen, Atlas, and Lanner in '92. But it seems very simple. It's really mellow, and so it wasn't very popular for a while. But it became popular. So the problem was also the main problem really is that it cannot tolerate noise, right? Because if you have a bit of noise, if I get an example who's labeled, but somehow if I get examples for which there is no perfect classifier, right, in my concept space, and I'm going to throw everything, it's not tolerant to noise really. Okay, so that's why it didn't become so popular. But actually, it became very popular after it was in 2006, there was a paper that robustified this algorithm. Okay, so it turns out that actually you can make it robust to noise. Okay, so how about the agnostic case or the target function might not belong to the search space? Can we do something interesting? Okay, and it turns out that actually, so this was the first paper that made this algorithm robust. Actually, it was my work joined with John Langford. And then Nabega Zimmer, right? And so it turns out that you can make this algorithm robust. And I'm not going to go through the details of this. I'm just going to tell you conceptually what's going on. And this is really interesting because it's really led to the first this was the first active learning algorithm that is general, it is robust to noise, and really led to so right now it made active learning a mainstream research area. And many people have followed up on it. Okay, so let me see what is the algorithm here. So actually it's a natural algorithm. Again, it's a natural robustification of the Cohen, Atlas, and Lanner algorithm. Now we cannot talk about the version space, but we can talk about a set of surviving classifiers, right? So at each moment in time, I'm going to have a set of surviving classifiers. Maybe this is my current set of surviving classifiers. I should have written here surviving classifiers. It's something like a version space, but it's not quite a version space. It's a set of classifiers with the property that the best classifier in the class is always guaranteed to be there. Okay, I'm going to set up the problem so that this happens. Okay, so I have a set of surviving classifiers, and we can again think about the region of disagreement. So we're going to go in rounds. We can think about what is the region of disagreement. And in each round, we're going to pick a few points at random, subject to being in the region of disagreement of the current set of surviving classifiers. Then we're going to query their labels. And what do we do with the query labels? We want to update our current set of surviving classifiers. And how do we do it? Well, we're going to throw out hypotheses from consideration from the current set of surviving classifiers if we are statistically confident that they are suboptimal. Okay, and there are many ways to instantiate this. And in our work, we did it in the following way. So what you can do, you can come up based on you query points at random from the current region of disagreement of the set of surviving classifiers. You can then use that to come up with upper and lower bounds on the error rates on the set of surviving classifiers. And then we're going to throw out classifier whose lower bound on the error rate is greater than the minimum upper bound, because you know it cannot be the optimal one. Okay? And then basically you get a new set of surviving classifiers. You can think about the region of disagreement and the light, and everything proceeds. Okay, this is the original algorithm. And in the original work, we basically showed that, actually, first of all, we showed that this doesn't suffer from selection bias, because we set up the things so that when we make our updates, somehow, we sample from the region of disagreement, and we get IID samples from the region of disagreement, and somehow we can be correct. This algorithm will end up being safe. So we can always show that it is never worse than passive learning in terms of label complexity. It's a safe algorithm. It's a correct algorithm, and we show that in certain interesting cases, like learning linear separators in high dimensions, it can get an exponential improvement in label complexity, even if you have noise over passive learning. Okay, these are our original results. Oops. But as I mentioned, there was a long line of work after. And it was an interesting algorithm, and so it generated a lot of work. And just the interesting fact is that basically led to very, very general understanding of what active learning can do for us. So now there is a very general, so for any hypothesis space, we can quantify the label complexity of this algorithm. And there have been, so for example, here's a simple one. It's based on the so-called disagreement coefficient, which it's this formula over here. The details are not important. I'm just going to mention to you what it means. So this disagreement coefficient just captures how quickly the region of disagreement collapses as you get closer and closer to the target function. Okay, which is very natural quantity to appear in this type of algorithm because we only sample points from the region of disagreement. Okay, and so then basically there are very generic sample complexity statements. Now the label complexity will look like this. So for instance, if you have no noise, it will be like based on this disagreement coefficient, and now we're going to have log 1 over epsilon as opposed to 1 over epsilon. So as long as this disagreement coefficient is small, as long as the region of disagreement collapses quickly, then you get exponential improvement in label complexity with this algorithm. And something similar happens when you have noise. Okay, which is good. Okay, cool. And so that's nice. So now, right. These are the results I'm talking about are very new results in the past 10 years. So now we have safe, very general active learning algorithms, but we are not quite done. And so this is great because we know that active learning we can quantify precisely how much active learning can help us in very general scenarios. So it's good. So that the plus is that there are algorithms that work for any concept class and the adversarial label noise. However, I think there is still research to be done there because there are two main problems here. First of all, these algorithms are not aggressive enough. We just query points from the region of disagreement, so we could potentially do even better. And actually, there's research showing that. Even in my own work, I showed that. Okay. And moreover, actually, the main problem from a practical point of view is that if we're thinking about about interesting cases like linear separators in RD, when the visit dimension is not constant, then these are computationally complex algorithms, right? So they are not scalable because how do we keep the set of surviving classifiers? How do we keep the region of disagreement, and so on? And actually, some of these papers that I mentioned, like there has been a long line of work here. Right, so actually, let me just mention, first of all, the algorithm is computationally efficient if you have classes of small VC dimension, like intervals, rectangles, if the VC dimension is constant. So if you have a search space that is not too large in size, then you can make this algorithm computationally efficient. So that's good news. On the other hand, for problems of the type we care about, like kernelized linear separators, then it's prohibitive computationally. Okay, and there has been some nice line of work trying to make this computationally efficient, and there are some nice results, for example, this paper by Dasgupta, Sumo, and Teleoni, where they somehow get a more efficient algorithm by somehow doing a reduction to passive learning, empirical minimization in passive learning, but still, I think, it's an open question to really come up with a clean, computationally efficient algorithm that gets the label complexity of these general results. So still an open question. So. But the cool thing is that now we know that active learning really helps, right? Because if active learning didn't really help, then why even design an algorithm, right? It really helps in very general scenarios when we have noise. And we have to do it in a kind of in an intelligent way. We cannot just rely on some, we cannot always rely on the most natural heuristics. Okay, cool. So I have a few more minutes. So first of all, any questions? Because this kind of finishes off the story of what's known in terms of formal guarantees. I want to spend a couple more minutes talking about other heuristics that people use in practice. But before that, do you guys have any questions?
Does the safe active only guarantee for the single distribution? If I draw the samples from two distributions and maybe one distribution is latent, so is it still useful using that safe?
So that's a great question. So there is a related area of research called transfer learning, where you maybe sample points from one distribution and you do active learning, maybe using that distribution, or maybe you can sample from two distributions, right? And yes, it's something called transfer learning, where you have one source distribution and a target distribution, for example, right? And the distributions, if they are somehow related, the question is, can you do active learning on the source or maybe the target together? Maybe you only have labeled examples from the source, but you want to do well on the target. Okay, and so it's called transfer learning, and actually my former postdoc, Ruth Urna, so she has formal results on that with safe procedures. It's called transfer learning, where you have a source distribution and a target distribution. Maybe you only get labeled examples from the source, but you want to do well on the target. And of course, would this be helpful? Well, if they are somehow related, the underlying distributions, and Ruth quantified. What does it mean? She has a paper we can find. Yeah, good. More questions? Yeah?
So all of the methods we talked about now draw random samples from the region of disagreement.
Yeah.
Are there strategies that like choose examples that they think would reduce the region of disagreement the most?
Yeah, so so in the realizable case, when we have noise-free scenario, there's something called a beautiful work actually by Sanjay Dasgupta, something called the splitting index, where he's exactly what he's trying to achieve. If you have no noise, you can also think about what would be the example that if I query the label, reduces the version spaces most. And he has a very nice a measure called the splitting index, which exactly quantifies that. When you have noise and you have general concept space, it's a bit harder. But for example, in my own work, I know that if you have linear separators and very nice distributions, you can be more aggressive than these general techniques. But somehow, at this point, we still use properties of the underlying distributions to set the bands. So you can do a margin-based technique rather than just being right. So the active SVM was very myopic. Just pick a point that is close to the current decision boundary. It's not really safe if you think about it, also because you might pick a noisy point, right? Plus the sampling bias that I mentioned. But what you can do something less myopic, you can maybe keep bands. You have a current guess for the target, you have a band around the current guess from the target, around the target. You pick a few points at random subject to be in the band, and then update. And then will be less sensitive to noise. Definitely is much more robust when you have noise. Now, how do you set the bands? At this point, we know how to set them when you have some nice distribution. So it's still an open question to set it in general to get the right label complexity. But those are also tolerant to noise. And actually, they're led to algorithms that are more tolerant to noise than people knew for passive learning. That's nice. Yeah?
I have a question. All of the examples that you gave assumed that there is an underlying P of X data distribution. We're getting a sample of those. And then the question is whether to request the label and so forth. Now, my question, and there really is a question, is there anything theoretically known about any theoretical results on the case where I don't have to wait for somebody to give me a sample of X. I can synthesize.
Oh yeah, absolutely. That's an excellent point. Actually, before this active learning literature, there's something called membership query model, where you can create your own example. Just pick your favorite example from the instance space. So there has been a lot of work showing that if you can create your own examples, actually you can overcome computational hardness. I mean, not only sample complexity, but there are problems that are computationally hard if you learn from random instances, but they are become computationally efficient if you can come up with your own examples. It's called learning membership queries. But that was not relevant from a practical point of view. So at the beginning of the 90s, there were papers showing that, for example, if you are doing image classification and if you create your own example, you want to distinguish man versus woman. And if you create your own example, you ask the expert, Travis, to label the example for you, and he'll not be able to label it. It's incomprehensible to him. Right? So that's why those algorithms become they've never been of practical relevance. So they became very relevant from a practical point of view. And so that's why people look at active learning, where you are only allowed to query for labels of examples that come from nature. Okay, so that's practically relevant. Okay, but that's excellent point. Cool, so I actually have 5, yeah?
I got a quick question. So what is the agreement region? Could you explain more about that? The agreement between
So if you have a set of surviving classifiers, a point is in the region of agreement if all the classifiers label that example in the same way. They all agree about the label. It's exactly what it means in English. If I have a set of classifiers H, a point X is in the region of the agreement of those classifiers if all the classifiers will label that example in the exact same way. They agree about the label.
Okay.
And the region of disagreement is a complement of the region of agreement. Cool. Actually, I want to spend a few more minutes. I have only a few more minutes left. I'll get more questions after. Yeah. But I want to just also just mention a few more other heuristics that people use in practice, right? Because you might wonder. So, for example, actually, I stole these slides from Jaime Carbonell. Right, so here's some other heuristics. So for example, maybe you still do kind of an SVM style of algorithm. You have some current guess for the target, maybe it's your current guess for the target. And so what you can do, you can think about, is there a cluster which I don't have any points from the cluster, large cluster. And I'm just going to maybe pick a point from the large cluster where I have no points, label points. Maybe I query this guy and then update my hypothesis. Okay, that's density-based sampling. Okay, I don't know any formal guarantees for this. I'm sure it can suffer from from sampling bias. Okay, but it will be interesting to understand when it does well. Okay, another one is this jump that I mentioned, the active SVM, pick the point close to the current decision boundary, and we've seen can do really poorly sometimes. Another one would be just to increase diversity, maybe actually pick the point that is maximally distant from all the label points. Okay? It's again another heuristic. To be also interesting to understand on it as well. Okay, and I also have a couple, just one more minute I want to take, and Travis will follow this in the recitation. I also want to mention another very interesting class of algorithms, active learning algorithms that are based on the graph-based semi-supervised learning that we talked about last time. And Travis will go through all those details in the recitation. So if you guys remember, in the graph-based semi-supervised learning, the implicit assumption is that we have a similarity function, and similar examples have similar labels. Right? And so, for example, why is it helpful? Because maybe I know the label of this guy. I have no idea what is the label. I know the label of this guy. I have no idea what is the label of this guy. But then for a chain of unlabeled example similarities, I can quickly infer that this must be a 2-2. Yeah, it's also a digit 2. Okay, so based on this idea, then this graph-based semi-supervised learning technique was we create a graph. We put the nodes. The graph are all my samples. Some of them are most of them are unlabeled, like this all over here. Maybe a couple of them are labeled. And then what we said we do algorithmically, we're going to try to find a partitioning of the graph that basically has the property that all the labeled examples of the same class are in one part, and the weight of the edges across the cut is minimized, right? Because it captures exactly that similar examples must have similar labels. And as I mentioned, there are many algorithms that people have looked at. The original paper by Avrim and Shuchi kind of did a hard partitioning, but it was efficient only when you have two labels. And there was a very interesting work by John Lafferty, Jerry Zhu, and Zubin Garamani, where they relaxed this constraint a bit, so they now can handle many, many classes. And the key point there was to somehow relax, rather than forcing the algorithm to output a hard labeling of the points, will be allowed to output a soft labeling. So for example, if I have only two labels, I'm going to put a probability distribution. So P of, will be f of x for point x will be what's the probability that that example is labeled 1. And 1 minus f of x is probability that is labeled 0. Okay, and then what you want to do then, given this, the objective function that they solve for, we are trying to find the soft labeling of the graph that enforces agreement with the labels, although not strict enforcement, but somehow enforces some agreement with the labels, and has the property when similar nodes get similar labels, similar probabilistic labels. Okay, and it turns out that if you have semi-supervised learning, then you can solve this. You can solve for this soft labeling by using a system of linear equations. And again, Travis will discuss that. I just want to mention, this is my second to last slide. I want to mention that you can use this algorithm, and it's commonly used in practice. You can make it active. And the idea would be, we first build a neighborhood graph, then we query a few points at random, maybe I get a negative example and a positive example. Then I run the semi-supervised procedure to come up with a soft labeling of the examples. Right? So maybe this example will be 0.5. I'm truly uncertain if it should be 1 or 0. Maybe this is 0.8. I'm kind of certain it should be 1, and so on, right? I come up with a soft labeling, and then you can use this soft labeling to decide what example to query next. Now, one simple solution would be, well, let me just query this example over here, because I'm the most uncertain about it. It's like the uncertainty is 0.5. Yeah, but in this specific example, because I also want to exploit the fact that similar examples have similar labels, that's not a good idea, because this guy is really isolated over here. And if I query the label, it doesn't give him any more information about the other points. So instead, you might want to pick a more central node, like this one, 0.6 over here, because if I get this label, maybe I somehow get a lot more information about the rest. And we have a specific procedure where it's a one-step look ahead, and Travis will go through this in the recitation concretely. I'm not going to go through it right now, but I just want to mention that there are no theoretical guarantees known about this technique. I think it's very interesting. I think it should be analyzable, actually, now that I think about it. And also does very well in practice. For example, we used it for video segmentation, and people have used it for other applications. Okay, cool. Because I'm out of time, just to summarize, so active learning, I think it's a really important modern learning paradigm. And there are many common heuristics for active learning. However, those common heuristics often suffer from the sampling bias, so you really have to be careful. But luckily, there's been a lot of interesting research providing safe active learning procedures. At this point, they are not all of them computationally efficient, but there has been great progress, and there is a high hope that we're going to come up with general purpose active learning procedures that will do well. And right, in terms of things that you should know, some of these common heuristics, the idea of what you choose to sample and so on, and also maybe a little bit about safe disagreement-based active learning. Cool. So, any questions? Any more questions? Okay, great.